What if I told you that a single misunderstanding about how a switch, router, or IP address works can cost you multiple questions on the CCNA exam? Thousands of candidates spend weeks memorizing commands, only to discover that they never truly understood the networking fundamentals everything else is built on. If you want to avoid that mistake and build real confidence for exam day, stay with me until the end of this lesson. And don't forget, you can download a free CCNA study guide with the most important exam questions from the link in the description. Now, let's begin with the foundation of every successful CCNA journey. In this first section, you'll master the networking fundamentals and network access concepts that every Cisco networking professional needs to understand. We'll explore the essential devices that power today's networks, including routers, switches, wireless access points, and the different types of network cables that connect them. Instead of simply memorizing definitions, you'll learn how these devices work together to move data across a network. This strong foundation will make the more advanced CCNA topics much easier to understand as you continue through the course. By the end of this section, you'll be able to identify the major network components, explain their purpose, and understand how data travels from one device to another. These are the core concepts that appear throughout the CCNA exam and in real-world networking careers. So, if you're ready to build the knowledge that every network engineer starts with, let's dive into the fascinating world of Cisco networking. Let us start by defining what a computer network actually is, so we have a clear starting point. At its simplest, a network is a group of two or more devices connected together to share resources and communicate with one another. These devices, which we often call hosts or endpoints, can be anything from the laptop you are using right now to smartphones, printers, or massive enterprise servers. In the real world, networks allow employees to share files, access the internet, and collaborate securely across different office locations. Whenever you hear the term endpoint on the CCNA exam, just remember it refers to these everyday user devices that send and receive data. To connect all these endpoints together within a single building or office space, we use a specialized device called a network switch. A switch acts as a central meeting point for all the cables coming from computers, printers, and servers in a local area. Think of a switch like an extremely smart traffic cop standing at a busy intersection, directing cars exactly where they need to go without causing collisions. When a computer sends data into the switch looks at the destination address and forwards the data only to the specific cable connected to the receiving computer. This targeted forwarding makes switches incredibly efficient and forms the backbone of what we call a local area network. While switches are fantastic at connecting devices within the same office, they cannot send data to completely different networks, which is where routers come into play. A router is a highly intelligent network device designed specifically to connect multiple different networks together, such as connecting your home or office network to the public internet. If a switch is like a local traffic cop, a router is like an airport transit hub that figures out the best possible path to send cargo across the world. Whenever a computer wants to talk to a server that is not on its local switch, it sends the data to the router, and the router handles the long-distance delivery. For your exam, always remember that switches operate locally, while routers connect different networks globally. Moving beyond basic connectivity, modern networks also require specialized devices to keep them safe from outside threats, which brings us to firewalls. A firewall sits at the very edge of your network, usually right next to your router, and acts as a strict security guard checking everyone who tries to enter or leave. It examines all the data traffic flowing through it and uses a set of predefined security rules to either block malicious traffic or allow safe traffic to pass. In enterprise environments, Cisco firewalls are incredibly popular because they can inspect data deeply and stop advanced viruses or hackers before they ever reach the local switches. Understanding the role of a firewall is essential, as security is integrated into almost every single topic on the modern CCNA blueprint. Now that we know about the devices, let us talk about the physical cables that connect them all together, starting with copper cabling. Unshielded twisted pair, commonly known as UTP cable, is the most standard type of copper cable you will see in any office environment. Inside a UTP cable, there are 8 tiny copper wires twisted together in pairs, and this twisting is a clever engineering trick that actually helps prevent electrical interference from ruining the data signal. Copper cables are cheap, highly flexible, and perfect for connecting employee computers to the network switch located down the hall. A great exam tip is to remember that standard copper Ethernet cables have a strict maximum length limit of exactly 100 meters before the data signal becomes too weak. When we need to send data much farther than 100 meters, or when we need incredibly high speeds, we leave copper behind and use fiber optic cabling. Instead of using electrical pulses over copper wires, fiber optic cables use tiny pulses of light traveling through extremely thin strands of flexible glass. Because it uses light, fiber optic cabling is completely immune to electromagnetic interference, meaning you can run it safely next to heavy factory machinery or power lines without dropping any data. Fiber is typically used to connect different equipment rooms together, to link entire buildings on a campus, or to connect high-speed data centers. The CCNA exam will often test your knowledge on when to choose fiber over copper, so always associate fiber with long distances, high speeds, and immunity to electrical interference. How we physically arrange and connect all these cables and devices is known as a network topology, and the most common one you will encounter is the star topology. In a star topology, all the endpoint computers and devices connect individually to a central switch, making the layout look somewhat like a star pattern. The beauty of this design is that if one single cable breaks, only that specific computer loses connection, while the rest of the network continues operating perfectly. This makes troubleshooting extremely easy, because network administrators can quickly identify exactly which cable or switch port is causing a problem for a user. Almost every modern local area network uses the star topology, making it a foundational concept you must know for the certification. As networks grow larger and require more reliability, we often move toward a modern variation called the spine and leaf architecture. In traditional highly connected topologies, engineers ran cables everywhere to ensure that if one cable failed, the data simply took another path. Because running that many cables is too messy for regular offices, this highly connected design is beautifully organized in modern data centers using the spine and leaf method. Every leaf switch connects to every spine switch, providing massive redundancy and ensuring data always travels exactly the same distance to reach its destination. Whenever you see exam questions about maximum reliability, modern data centers, and redundant paths, you should immediately think of the spine and leaf design. To truly understand how data moves through these topologies, you need to understand the language of networks, which is organized by the TCP/IP conceptual model. The TCP/IP model breaks the complex process of networking down into 4 distinct layers, which are the application layer, the transport layer, the internet layer, and the network access layer. By breaking networking down into layers, engineers can easily troubleshoot problems because they can test one specific layer at a time without worrying about the others. When data is sent from your computer, it moves down through these layers, getting packaged with specific instructions at each step before finally becoming electrical signals on the wire. Mastering the layers of the TCP/IP model is an absolute requirement, as the entire Cisco curriculum is built completely around this layered approach. At the bottom of this process, dealing directly with the local switches, we have something called a Media Access Control Address, or MAC address. A MAC address is a unique physical identifier permanently burned into the network card of every single computer, smartphone, and printer by the manufacturer. Unlike a home address that can change if you move, a MAC address never changes, and it serves as the permanent physical name of that specific hardware device. Local network switches rely entirely on these MAC addresses to quickly figure out which physical port they should forward the data frames to. Always remember for the exam that MAC addresses operate strictly on the local network, and they are formatted as a 48-bit hexadecimal number. While MAC addresses are perfect for local switch delivery, we need a different type of address to send data across the global internet, which is the IP address. Specifically, Internet Protocol version 4, or IPv4, uses a logical 32-bit address separated into 4 distinct blocks of numbers. Unlike a permanent MAC address, an IP address is logical, meaning it changes depending on what network you connect to, exactly like how your zip code changes when you move to a new city. Routers use these IP addresses to read the destination network and determine the best geographical path to deliver the data packet across the world. You will spend a significant amount of your career configuring, troubleshooting, and designing IPv4 addressing schemes, so getting comfortable with them is crucial. Every single time you configure an IPv4 address on a device, you must also provide a companion piece of information known as a subnet mask. The subnet mask is a special number that acts like a decoder ring for the computer and the router, helping them figure out exactly which part of the IP address represents the overarching network, and which part represents the specific host device. By looking at the subnet mask, a computer can instantly tell if the destination it wants to reach is sitting on the local switch, or if it needs to send the data to the router for remote delivery. Understanding how the subnet mask divides an IP address is the foundation of subnetting, which is widely considered the most important math skill you will learn for the CCNA. Because the world essentially ran out of available IPv4 addresses due to the explosion of internet-connected devices, engineers created a modern replacement called IPv6. An IPv6 address is massive, using 128 bits written in long hexadecimal strings, which provides an almost infinite number of unique addresses for future technologies. Aside from simply providing more addresses, IPv6 also includes improvements that eliminate the need for certain complex network translations that we used to rely on. Do not let the long strings of numbers intimidate you, because the core routing concepts of IPv6 are actually very similar to the IPv4 concepts you already know. The exam will definitely test your ability to identify valid IPv6 addresses and understand how they can be abbreviated by removing consecutive zeros. When data actually travels across a standard local network cable, it is packaged into a standardized digital envelope called an Ethernet frame. This frame encapsulates the raw data and slaps on a header that contains the source MAC address of the sender and the destination MAC address of the receiver. It also includes a special section at the very end of the frame called a frame check sequence, which acts as a mathematical quality control check to ensure the data was not corrupted by electrical noise during transit. If a switch receives an Ethernet frame and the mathematical check fails, it simply throws the damaged frame in the trash to protect the network from processing bad data. Understanding the basic structure of an Ethernet frame helps you visualize exactly what switches are looking at when they process millions of messages per second. Network access is not just about physical cables anymore, so the CCNA heavily emphasizes the fundamentals of wireless networking using Wi-Fi. Instead of cables, wireless networks use invisible radio frequency waves to transmit those same Ethernet frames through the air between a user device and a wireless access point. A wireless access point essentially acts as a bridge, catching the invisible radio signals from laptops and converting them into electrical signals to send down a physical copper cable to the switch. Wireless introduces unique challenges like signal interference from thick walls or other electronics, which network engineers have to carefully plan around when designing a wireless deployment. Just remember that a wireless network is simply a physical network extended into the air, and it still relies on all the same core concepts like MAC addresses and IP addresses. A fantastic technology that brings wireless access points, switches, and cabling together is called Power over Ethernet, or simply PoE. PoE is a clever standard that allows a network switch to send electrical power over the exact same copper UTP cable that is already carrying the data signals. This means you can mount a wireless access point or a security camera on the ceiling without having to hire an electrician to install a dedicated power outlet up there. The switch intelligently negotiates with the connected device to figure out exactly how much electrical wattage it needs, ensuring it powers the device safely without frying the internal circuits. This is a massive cost-saving technology in enterprise networks, and you will frequently see exam questions asking about the benefits and applications of Power over Ethernet. Once your network is connected and addressed, you need a way to test if it is actually working, which brings us to fundamental troubleshooting tools like Ping and Traceroute. Ping is a simple command line tool that sends a tiny probe message to a destination IP address and waits for a reply, instantly telling you if the remote device is online and reachable. Traceroute is slightly more advanced, as it not only tells you if the destination is reachable, but it also lists every single router hop the data took along the journey to get there. If a user complains they cannot reach a specific server, running a traceroute will show you exactly which router along the path is failing or dropping the traffic. These two commands are the absolute best friends of any network engineer, and you will use them on a daily basis in the real world. To summarize how all these fundamentals work together, imagine an employee sending an email from their laptop. The laptop creates the data, packages it with a destination IP address, wraps it in an Ethernet frame with the local router's MAC address, and sends it as electrical signals down a copper cable. The local switch receives the frame, reads the MAC address, and instantly forwards it out the correct port to the local router. The router receives it, strips off the old frame, looks at the destination IP address, and uses its intelligence to forward the packet across fiber optic links toward the internet. This beautiful, coordinated dance of encapsulation, switching, and routing happens billions of times a second in networks worldwide, and you now understand the mechanics behind it. Congratulations on completing this highly informative section on networking fundamentals and network access. To truly lock in this new knowledge, I highly encourage you to complete the attached practice test immediately while the concepts are still fresh in your mind. Research shows that answering practice questions dramatically improves your long-term retention and heavily increases your overall exam readiness. Remember that the practice test is included right here with this lesson, so take advantage of it to actively challenge your understanding of switches, routers, and addressing. Keep up this fantastic momentum, stay actively engaged with the material, and I will see you in the next section where we dive deep into IP connectivity and routing technologies. Welcome back, and congratulations on reaching the second section of our course, focusing entirely on IP connectivity and routing technologies. In this lesson, you will learn exactly how routers make intelligent decisions to send data across complex networks and the internet. Understanding these routing concepts is incredibly important because without them, isolated local networks would never be able to communicate with the outside world. I am excited to share these mechanics with you, as routing is truly the heart of global communications and a major focus of your exam. Get comfortable, prepare to expand your networking knowledge, and let us explore how data finds its way across the globe. At the core of IP connectivity is the router, a highly specialized computer designed to forward data packets between different networks. While local switches look at physical MAC addresses, routers operate at the network layer and look strictly at logical IP addresses. When a router receives a packet of data, it opens the digital envelope, reads the destination IP address, and decides the best possible path to send it forward. You can think of a router as a postal sorting facility that looks at the zip code on a letter and puts it on the correct delivery truck. The CCNA exam heavily tests your understanding of this exact packet forwarding process. To make these intelligent forwarding decisions, every router relies on a fundamental database called the routing table. The routing table is essentially a map stored inside the router's memory that lists all the known network destinations and the specific physical interfaces required to reach them. Whenever a packet arrives, the router checks the destination IP address against this internal map to find a matching entry. If a match is found, the router sends the packet out the correct interface toward its destination. If the router checks the table and finds no matching destination at all, it simply drops the packet and discards the data entirely. The simplest type of entry found in a routing table is a directly connected network. The moment you assign an IP address to a router interface and turn that interface on, the router automatically adds that specific network directly into its routing table. The router instantly knows how to reach devices on this local link because it is physically plugged into that exact network segment. You do not have to configure any special protocols for directly connected routes to work, making them the foundational building blocks of all routing operations. A common exam tip is to remember that a router will always prefer a directly connected route over any other type of path. When a router needs to reach a network that is not directly connected to it, network engineers can use a method called static routing. Static routing involves an administrator manually typing a specific command to tell the router exactly which path to take to reach a remote destination. This manual approach gives you absolute control over traffic flow and consumes almost zero extra processing power on the router hardware. However, the major downside to static routes is that they cannot automatically adapt if a cable breaks or a network goes offline. You will primarily see static routing used in very small, simple networks where the physical layout rarely changes. A highly useful variation of a static route that you must know for the certification is called a default route. A default route acts as a universal backup plan, telling the router where to send data when the destination does not match any other specific entry in the routing table. We often call this the gateway of last resort, and it is almost always pointed directly toward the internet service provider. Instead of a router trying to memorize every single website address in the world, it simply sends all unknown internet traffic out the default route. Setting up a default route is a massive time saver and keeps the routing table beautifully small and efficient. Since a router can learn about the exact same destination from multiple different sources, it uses a concept called administrative distance to decide which source is the most trustworthy. Administrative distance is simply a believability score, represented by a number from 0 to 255, where a lower number indicates higher trust. For example, a manually configured static route has an administrative distance of 1, making it highly trusted, while dynamic protocols have higher numbers like 90 or 110. If a router learns 2 paths to the same server, it will always install the path from the source with the lowest administrative distance into the routing table. Memorizing the default administrative distance values for different routing protocols is a guaranteed way to earn points on your exam. Sometimes a router learns multiple paths to the exact same destination using the exact same routing protocol, which introduces a new tiebreaker known as a metric. While administrative distance measures the trustworthiness of the source, the metric measures the actual physical quality or length of the specific path. Different routing protocols use different mathematical formulas to calculate this metric, with some counting the number of router hops and others looking at the speed of the cables. When faced with multiple equal paths from the same protocol, the router will always choose the path with the lowest overall metric score. Understanding the clear difference between administrative distance and metric is a critical concept that trips up many beginners. While static routes are great for small setups, enterprise environments require networks that can heal themselves, which is where dynamic routing protocols come in. Dynamic routing involves routers speaking a specialized language to automatically share their network maps with other neighboring routers. If a construction crew accidentally cuts a major fiber optic cable, dynamic routing protocols instantly detect the failure, calculate a brand new path, and automatically update the routing tables. This incredible ability to automatically adapt to network changes makes dynamic routing the absolute standard for large organizations. The Cisco blueprint focuses heavily on your ability to configure and troubleshoot these automatic routing behaviors. Within the world of dynamic routing, there are 2 primary categories of protocols known as distance vector and link state. Distance vector protocols are somewhat older and simpler, making routing decisions based purely on how far away a network is and what direction to send the data. They operate much like reading road signs on a highway, knowing the destination is 50 miles ahead, but never seeing the full map. Link state protocols are much more advanced because every router builds a complete, detailed mathematical map of the entire network inside its memory. This full picture allows link state protocols to make highly accurate and incredibly fast decisions when network topology changes occur. The most important dynamic routing protocol you need to master for the CCNA is Open Shortest Path First, universally known as OSPF. OSPF is a highly popular link state routing protocol used by nearly every major enterprise because it is an open standard, meaning it works on Cisco devices and non-Cisco devices alike. When you enable OSPF, the router immediately starts sending friendly hello messages out of its interfaces to discover other OSPF-speaking routers nearby. Once these neighbor relationships are formed, the routers securely exchange their local network information to build a complete, unified map of the enterprise. OSPF is a massive topic on the exam, so you should pay close attention to how it successfully forms these neighbor relationships. To keep the OSPF routing calculations fast and efficient in massive networks, the protocol uses a clever hierarchical design built around different geographic areas. Instead of every router trying to memorize every single detail of a massive global network, administrators group routers into specific numbered OSPF areas. The most important rule to remember is that every OSPF deployment must have a backbone area, which is always configured strictly as Area 0. All other secondary areas must physically connect directly into this backbone Area 0 to successfully share routing information. This hierarchical area design minimizes processing power on the routers and limits the negative impact if a network link rapidly bounces up and down. When OSPF calculates the absolute best path to a destination, it relies on a specific metric called cost. The OSPF cost is directly tied to the bandwidth speed of the physical interfaces along the path, meaning faster links get a better, lower cost score. Because OSPF always prefers the lowest cost path, it will automatically choose a high-speed gigabit fiber link over a slow copper connection every single time. As a network engineer, you can manually adjust this cost value on an interface to artificially steer network traffic exactly where you want it to go. Knowing how OSPF calculates cost based on interface bandwidth is a concept that appears frequently in scenario-based certification questions. Moving slightly beyond basic routing, We must also consider how endpoint devices handle router failures, introducing the concept of first-hop redundancy protocols. Normal computers are typically configured with only one default gateway IP address, meaning if their local router fails, they completely lose all internet access. First-hop redundancy protocols solve this problem by allowing two separate physical routers to join together and share a single, imaginary IP address. The computers point their default gateway to this shared virtual IP address, completely unaware that two different physical routers are actually managing it behind the scenes. This guarantees that if the primary router suddenly loses power, the backup router instantly takes over without the computers ever noticing a disruption. The specific first-hop redundancy protocol created by Cisco that you need to study is called Hot Standby Router Protocol, or HSRP. In an HSRP setup, one router is elected as the active router that handles all the daily traffic, while the other sits quietly as the standby router. The standby router constantly listens for specialized hello messages from the active router to confirm it is still alive and functioning normally. The exact moment those hello messages stop arriving, the standby router promotes itself to the active role and immediately begins forwarding the network traffic. HSRP provides seamless network survival during hardware failures, making it a highly tested topic for modern network design. Another fundamental routing concept bridges the gap between local switches and remote networks, known as inter-VLAN routing. In enterprise networks, administrators separate different departments into isolated logical networks called VLANs for security, meaning the accounting computers cannot normally talk to the sales computers. Because these VLANs act like completely separate networks, you absolutely must use a routing device to allow communication between them. The classic, traditional method for doing this involves connecting a router to a switch with a single physical cable, a design playfully known as router on a stick. Understanding how a router passes traffic between separated VLANs is an essential skill for managing secure local area networks. To make that router on a stick configuration actually work, engineers use a clever software trick called subinterfaces. Instead of buying a router with 20 expensive physical ports for 20 different VLANs, you take one physical router port and logically slice it into 20 virtual subinterfaces. Each virtual subinterface acts as the default gateway for a specific VLAN and uses a tagging standard called 802.1q to keep the data properly separated on the physical wire. When the router receives a tagged data frame from the switch, it reads the tag, removes it, routes the packet internally to the correct subinterface, and sends it back down the wire. You will definitely see configuration questions regarding subinterfaces and 802.1q tagging on your test. While the router on a stick method is great for learning, modern enterprise networks handle inter-VLAN routing much faster using Layer 3 switches. A Layer 3 switch is an incredibly powerful hybrid device that combines the high-speed physical ports of a normal switch with the logical brains of a traditional router. Instead of sending traffic over a physical cable to an external router, the Layer 3 switch uses internal software interfaces called switch virtual interfaces to route the traffic instantly. This internal routing happens at wire speed using specialized hardware chips, making it vastly superior for large office buildings with thousands of communicating computers. The exam will definitely expect you to know that Layer 3 switches provide the fastest possible inter-VLAN routing. Once your routing protocols and default gateways are configured, you will use specific command line tools to verify everything is operating perfectly. Your most powerful tool is the show IP route command, which instantly prints the entire routing table directly onto your terminal screen. By reading this output, you can quickly verify if your OSPF neighbor relationships formed correctly and if your static routes are typed properly. If a network path is missing from this output, you know immediately that you have a configuration issue preventing the router from learning the destination. Becoming highly comfortable reading and interpreting the output of the show IP route command is arguably the most valuable practical skill you can develop for your networking career. Excellent work completing this comprehensive section on IP connectivity and routing technologies. I strongly encourage you to take the attached practice test right now to validate your understanding of static routes, OSPF, and the routing table. Answering practice questions is the single best way to improve your memory retention and ensure you are fully prepared for exam day. Please remember that the practice test is completely included with this lesson, so use it to actively test the concepts you just learned. Keep up your fantastic dedication to studying, and I will see you in the next section where we will tackle switching, VLANs, and Layer 2 protocols. Welcome to the third section of our comprehensive exam preparation journey, where we focus heavily on switching, virtual local area networks, and Layer 2 protocols. In this phase of the course, you will learn exactly how local networks are constructed, segmented, and protected against catastrophic failures. Understanding these switching technologies is incredibly important because they form the physical foundation that every single user device relies on to connect to the network. We are going to explore how switches manage traffic internally and discover the ingenious protocols that keep everything running smoothly without manual intervention. Get ready to master the local area network, because these concepts are heavily featured on the certification exam and are essential for any network engineer. Let us begin by looking closely at how a modern network switch actually operates on a daily basis. Unlike a simple hub that blindly copies data out of every single port, a switch is highly intelligent and operates securely at layer 2 of the network model. A switch cares exclusively about physical MAC addresses, which are those permanent hardware identifiers attached to your computer network card. By paying strict attention to these MAC addresses, a switch can isolate conversations so that data flowing between two specific computers does not bother anyone else on the network. This ability to provide dedicated bandwidth to every single connected device is exactly why switches completely revolutionized local networking. To perform this intelligent forwarding, a switch relies entirely on an internal database called the MAC address table. When you turn on a brand new switch, this table is completely empty, meaning the switch has no idea where any computers are located. However, the moment a computer sends a piece of data into the switch immediately examines the source MAC address attached to that incoming frame. The switch records that source MAC address and associates it with the physical port the data just entered through, effectively memorizing the exact location of that specific computer. By constantly listening to the source addresses of incoming traffic, the switch automatically builds a highly accurate map of the entire local network. Once the switch has populated its MAC address table, it can make incredibly fast decisions about where to send traffic. When a data frame arrives, the switch looks at the destination MAC address and checks its internal table to see if it knows which port that device is connected to. If the switch finds a matching entry in the table, it instantly forwards the data strictly out of that one specific port, ignoring all the others. But if the switch does not know where the destination is located, it takes a safe guess and floods the data out of every single port except the one it arrived on. This flooding behavior guarantees the data reaches its target, and once the target replies, the switch immediately learns its location for next time. While switches are highly efficient, having hundreds of computers connected together creates a massive problem known as a large broadcast domain. A broadcast is a special type of message meant for everyone, like a computer shouting out a request to find a local printer. Switches are forced to forward these broadcast messages out of every single active port, meaning every computer is forced to pause and process the noise. If a network grows too large, the sheer volume of background broadcast traffic can severely slow down the entire system and degrade performance for the users. As a network administrator, it is your job to solve this noise problem and break large networks down into smaller, manageable pieces. The ultimate solution to controlling broadcast noise is an incredible technology called a virtual local area network, universally known as a VLAN. A VLAN allows network engineers to take one large physical switch and logically slice it into multiple smaller virtual switches using only software commands. When you assign different switch ports to different VLANs, you create strict, invisible boundaries that prevent broadcast traffic from crossing over. A computer shouting for a printer in VLAN 10 will never be heard by a computer sitting in VLAN 20, even if they are physically plugged into the exact same switch. The exam heavily tests your understanding of how VLANs isolate traffic, so always remember that they effectively break up large broadcast domains. Beyond simply controlling network noise, VLANs provide massive benefits for both network organization and corporate security. In a typical office building, you can use VLANs to group users logically by their job function, rather than grouping them by where the desk is physically located. For example, you can assign all the human resources computers to one secure VLAN, and place all the guest lobby computers into a completely separate, restricted VLAN. This logical separation means a malicious guest sitting in the lobby cannot accidentally access sensitive payroll servers, because the switch physically blocks the traffic from crossing the VLAN boundary. Understanding the practical security benefits of VLAN separation is a core concept you must grasp for the certification. When connecting standard endpoint devices like desktop computers or printers to a switch, you configure the switch port as an access port. An access port is uniquely designed to belong to only one specific VLAN at a time, keeping things extremely simple for the connected computer. The computer has no idea that VLANs even exist. It simply sends its standard internet traffic into the switch, completely unaware of the underlying network architecture. The switch receives the data on the access port, internally labels it as belonging to that specific VLAN, and ensures it stays isolated from other departments. For your exam, always associate access ports with single endpoint devices and single VLAN assignments. While access ports are perfect for connecting individual computers, a significant problem arises when you need to connect two entire switches together. If you have computers in VLAN 10 and VLAN 20 spread across multiple different floors in a building, you need a way to pass all of that separated traffic between the switches. You could theoretically run a separate physical cable for every single VLAN, but that would quickly waste all your expensive switch ports and turn your wiring closet into a nightmare. Network engineers needed a clever way to carry multiple different VLANs across a single physical cable, which introduces the essential concept of trunking. To solve this problem, we configure the connection between two switches as a trunk port, which is capable of carrying traffic for dozens of different VLANs simultaneously. To keep the traffic separated while it travels across this shared cable, the sending switch injects a tiny digital label into the Ethernet frame, a process governed by the 802.1q standard. This specialized label tells the receiving switch exactly which VLAN the data belongs to, allowing it to correctly forward the traffic to the appropriate access ports on the other side. You will absolutely need to know the 802.1q tagging standard for the exam, as it is the universal method used to manage trunk links across modern enterprise networks. An important nuance of the 802.1q standard that frequently appears on certification exams is the concept of the native VLAN. By default, trunk ports are configured to send one specific VLAN across the link without attaching any digital tag at all, and this untagged traffic belongs to the native VLAN. The original purpose of the native VLAN was to support legacy network devices that did not understand modern tagging protocols, but today it primarily presents a security risk if not managed correctly. Security best practices strongly dictate that you should change the native VLAN away from the default setting of VLAN 1 to prevent potential unauthorized access. Understanding the difference between tagged traffic and untagged native VLAN traffic is crucial for troubleshooting switch connections. Cisco switches feature an automatic negotiation system called the Dynamic Trunking Protocol, or DTP, which attempts to figure out if a port should act as an access port or a trunk port. When you plug two Cisco switches together, they can use DTP to automatically form a trunk link without the administrator having to type any manual configuration commands. While this sounds incredibly convenient, relying on automatic negotiation is actually considered a major security vulnerability in production environments. A clever attacker could theoretically plug a laptop in and trick the switch into forming a trunk, gaining unauthorized access to every single VLAN in the building. As a certified professional, you should always manually configure your switch ports and proactively disable automatic DTP negotiations. Another Cisco proprietary feature designed to save administrators time is the VLAN trunking protocol, commonly referred to as VTP. In a large campus network with 50 different switches, manually creating VLAN 10 and VLAN 20 on every single device would be tedious and prone to human error. VTP allows you to create all your VLANs on one central server switch, and it automatically synchronizes that exact VLAN database out to all the other switches in the network. While it saves time, a simple configuration mistake on the central server could accidentally delete every VLAN across the entire company in seconds. Exam questions will test your knowledge of the different VTP modes, specifically the server, client, and transparent modes. As we design larger networks using multiple switches and trunk links, we must build in redundancy to ensure the network stays online if a cable fails. Engineers do this by connecting multiple switches together in a physical circle, so if the primary path breaks, the data simply travels the opposite direction around the loop. Unfortunately, because switches constantly flood broadcast traffic to find unknown destinations, These circular physical loops cause catastrophic events known as broadcast storms. Broadcast frames will bounce around the circular loop forever, multiplying exponentially until the network equipment completely crashes under the massive processing load. We need physical redundancy, but we absolutely must prevent these logical switching loops from destroying the network. The ultimate hero that saves our networks from these disastrous loops is called the Spanning Tree Protocol, or simply STP. Spanning Tree Protocol is an automated background process that maps out the entire physical topology of your switches and actively searches for any circular loops. When it discovers a loop, STP automatically shuts down a specific switch port, placing it into a blocking state to break the continuous circle. The absolute brilliance of STP is that if a main cable suddenly breaks, the protocol detects the failure and automatically unblocks the backup port to restore connectivity. STP provides the perfect balance, allowing you to plug in redundant cables for safety without causing catastrophic broadcast storms. To figure out exactly which ports to block and which ports to leave open, STP forces all the switches to hold an election to choose a leader, known as the root bridge. Every switch shares its unique identifier, called a bridge ID, which is a combination of a configurable priority number and the permanent MAC address of the switch hardware. The switch with the absolute lowest bridge ID wins the election and becomes the central reference point for the entire network topology. Once the root bridge is elected, all the other switches calculate the shortest and fastest path to reach the leader and block any extra alternative paths. Understanding this election process and knowing that the lowest bridge ID always wins is a guaranteed test concept. When you plug a computer into a switch running traditional spanning tree, the port does not turn on instantly, but instead transitions through several specific listening and learning states. During these transitional states, the switch intentionally pauses traffic for up to 30 seconds to ensure that turning on this new port will not accidentally create a devastating loop. While waiting 30 seconds is necessary to protect the network from loops, it can be extremely frustrating for users waiting for their computers to acquire network addresses and connect to the internet. The exam will definitely expect you to recognize these STP port states and understand why the protocol intentionally delays the forwarding of normal user traffic. Because a 30-second wait time is entirely unacceptable in modern high-speed networks, engineers developed an upgraded standard called Rapid Spanning Tree Protocol, or RSTP. Rapid Spanning Tree Protocol provides the exact same loop prevention benefits as the original version, but it is optimized to detect failures and transition ports in a fraction of a second. Instead of moving through slow listening phases, RSTP actively negotiates with neighboring switches to instantly determine if a path is safe to open. Almost every modern enterprise network uses Rapid Spanning Tree by default because of its vastly superior performance during network failures. You should be prepared to compare the slow transition timers of traditional STP against the lightning-fast convergence of modern RSTP. To further speed up network connections for endpoint devices, administrators use a critical STP feature called Port Fast. When you enable Port Fast on an access port connected to a single computer, you are telling the switch to completely bypass the normal 30-second listening phase and turn the port on immediately. However, to prevent someone from accidentally plugging a switch into a Port Fast enabled port and causing a loop, we always pair it with a protective feature called BPDU Guard. If a Port Fast port unexpectedly receives a spanning tree protocol message, BPDU Guard instantly shuts the port completely off to protect the network. Always remember the exam tip that Port Fast must strictly be used on edge ports connected to end-user devices, never on links between switches. You have done an outstanding job completing this vital section on switching, VLANs, and Layer 2 protocols. To fully solidify your understanding of these critical concepts, I highly encourage you to tackle the attached practice test right now. Working through practice questions will dramatically improve your ability to retain these technical details and ensure you are absolutely ready for your certification exam. Please keep in mind that the practice test is completely included alongside this lesson for your convenience, so be sure to take advantage of it to measure your progress. Continue bringing this excellent focus to your studies, stay positive, and I will see you in the next section where we cover IP services and network management. Welcome to the fourth section of our course, focusing on IP services and network management. In this lesson, you will learn about the essential background protocols that keep networks running smoothly and allow administrators to monitor system health. Understanding these services is vital because they automate tedious tasks like assigning IP addresses and translating website names into numbers. I am thrilled to guide you through these topics, as they are the very tools you will use every single day to manage and troubleshoot real enterprise environments. Get ready to expand your technical toolkit, and let us explore the services that make modern networks so powerful and efficient. Up to this point, we have focused heavily on how to physically connect devices and route data between them. However, a functional network requires several supplementary services running quietly in the background to be truly useful for employees. Imagine forcing every new employee to manually configure their own IP address, subnet mask, and default gateway before they could check their email. That manual process would be an absolute nightmare for the IT department to manage, which is exactly why we rely on automated network services. These services eliminate human error and allow enterprise networks to scale effortlessly to support thousands of active users. The first critical service we need to understand is the Dynamic Host Configuration Protocol, widely known as DHCP. DHCP acts as an automated network administrator, instantly handing out IP addresses and configuration settings the moment a computer connects to the network. Instead of permanently hardcoding an IP address onto a laptop, the laptop effectively leases an address from the central DHCP server for a specific period of time. When the employee goes home for the day, that lease eventually expires, and the IP address returns to the available pool for another device to use. The CCNA exam expects you to fully understand the massive administrative benefits of this automated addressing system. To acquire an IP address, a client device and the DHCP server perform a four-step negotiation process commonly known as DORA. The computer first broadcasts a discover message to find any available DHCP server on the local network. The server hears this request and replies with an offer message, presenting an available IP address for the computer to consider. The computer then sends a request message to formally accept the offered address, and finally, the server sends an acknowledge message to finalize the lease. Memorizing these four steps in the exact order of discover, offer, request, and acknowledge is highly recommended for your certification test. Once a computer has an IP address, it needs a way to find resources on the internet using human-readable names, which introduces the Domain Name System, or DNS. Computers fundamentally only understand numbers, so they rely on IP addresses to locate remote servers, but humans prefer easy names like Cisco.com. DNS functions exactly like a massive digital phone book, instantly translating those memorable website names into the numerical IP addresses that routers actually understand. Without DNS, you would have to memorize a random string of numbers for every single website you wanted to visit, making the internet practically unusable for the general public. When you type a web address into your browser, your computer silently sends a DNS query to a specialized DNS server to ask for the corresponding IP address. The DNS server checks its massive database, finds the correct numerical address, and sends it back to your computer in a fraction of a second. Once your computer has that destination IP address, it can quickly package the data and send it to the default gateway for routing across the internet. You will frequently see exam questions asking you to specifically identify DNS as the primary service responsible for resolving hostnames to IP addresses. Another silent but incredibly important service running on your network devices is the Network Time Protocol, or NTP. NTP is carefully designed to completely synchronize the internal clocks of every single router, switch, and server across your entire organization to the exact same millisecond. It works by having your network equipment securely connect to highly accurate, centralized atomic clocks available on the internet or within your own data center. You might wonder why having the exact time matters so much for a router, but it is actually one of the most critical security and troubleshooting requirements in modern network architecture. When a network crashes or a security breach occurs, administrators have to read through thousands of device logs to reconstruct exactly what happened. If the clock on the firewall is 5 minutes faster than the clock on the core switch, trying to piece those event logs together into a logical timeline becomes completely impossible. Furthermore, modern digital security certificates rely entirely on precise expiration dates, meaning a device with an incorrect clock might suddenly block all secure web traffic. Understanding that NTP is absolutely essential for accurate log correlation and overall network security is a core concept you must grasp for the exam. Moving toward internet connectivity, we must discuss a fundamental technology that essentially saved the Internet from collapsing, called Network Address Translation, or NAT. As we discussed earlier, the world completely ran out of available public IPv4 addresses years ago, meaning we cannot give every single smartphone and laptop a unique public address. NAT solves this massive problem by acting as an invisible translator sitting on your edge router, between your private office network and the public Internet. It allows thousands of private, internal computers to safely share just one or two expensive public IP addresses to browse the web externally. The CCNA exam heavily tests your understanding of the specific terminology used to describe the NAT translation process. When talking about NAT, the internal IP address configured on an employee's actual computer is officially referred to as the inside local address. Conversely, the public IP address sitting on the outside of your router that the rest of the Internet actually sees is called the inside global address. These highly specific terms can be incredibly confusing at first glance, so you must carefully study the clear difference between the local, private perspective and the global, public perspective. The most common variation of this technology used in almost every home and small business is called Port Address Translation, or simply PAT. PAT is the specific network magic that allows 50 different laptops to surf the web simultaneously using only one single public IP address provided by the Internet company. The router achieves this by carefully tracking the unique source port numbers of every single internal data session, keeping everyone's web traffic perfectly separated in its memory. When you see scenario questions about allowing an entire office to access the Internet using a single public IP, the correct answer is almost always port address translation. As networks become more complex, they have to carry everything from simple text emails to real-time video calls on the exact same physical cables. Because network cables have maximum speed limits, during busy times of the day, data packets can actually get stuck in traffic jams waiting to be processed by the router. Quality of service, or QoS, is a set of configuration tools that allows you to identify highly important network traffic and immediately push it to the very front of the line. By configuring QoS, you guarantee that critical applications always receive the bandwidth they desperately need, even when the network is heavily congested with large file downloads. The most common reason engineers choose to implement quality of service is to strictly protect extremely sensitive traffic like Internet voice calls and live video conferences. If an email gets delayed by half a second due to temporary network congestion, the user will never notice or care. However, if a voice call packet gets delayed by that exact same half second, the phone call becomes jittery, robotic, and completely impossible to understand. Therefore, voice and video traffic must always be classified with the absolute highest priority using QoS, ensuring perfectly smooth communication for business operations. To properly manage all of these active protocols and hardware devices, administrators need a centralized way to monitor the overall health of the network using Syslog. Every time a router interface goes down, an OSPF neighbor relationship fails, or a cooling fan breaks inside a switch, the device generates a short text message explaining the exact event. Instead of forcing you to manually log into 50 different switches individually to read these messages, you can configure them to securely forward all their logs to a central Syslog server. This creates a highly organized, single pane of glass where you can instantly monitor the historical health of your entire infrastructure. Syslog messages are strictly categorized into 8 distinct severity levels, ranging from level 0 to level 7, which greatly helps administrators prioritize their daily troubleshooting efforts. Level 0 represents a catastrophic system emergency where the hardware is completely unusable, while level 7 is reserved strictly for highly detailed background debugging information. The certification exam frequently requires you to memorize these exact severity levels and their corresponding numbers to understand how critical a specific network alert truly is. As a highly useful exam tip, remember that lower severity numbers always indicate a much more severe problem that requires immediate attention from a qualified engineer. While Syslog is fantastic for text-based event alerts, we need a different protocol to pull detailed mathematical performance metrics from our devices, which is where SNMP comes in. The simple network management protocol allows a central monitoring server to constantly ask routers and switches for detailed numerical statistics, like current CPU usage or physical interface bandwidth levels. Using these continuous statistics, the monitoring software can automatically generate beautiful visual graphs that show exactly how busy a network connection is over a specific period of time. SNMP gives you the actionable data you need to proactively upgrade network links long before they become completely overwhelmed by heavy user traffic. Finally, when managing a completely unfamiliar network, engineers rely heavily on automated discovery protocols to figure out exactly how everything is physically connected together in the data center. Cisco Discovery Protocol, or CDP, is a proprietary software tool that allows Cisco switches and routers to automatically share detailed information about themselves with their directly connected neighbors. If you log into a switch and run a simple CDP command, it will instantly tell you the exact hardware names, management IP addresses, and physical port numbers of the devices plugged into it. Because CDP only works on specific Cisco hardware, the networking industry also uses an excellent open standard alternative called the Link Layer Discovery Protocol, or LLDP. When you begin designing these comprehensive services for real organizations, you will quickly find that advanced configuration scenarios demand a much deeper level of critical thinking. A common standard in modern enterprise engineering is that any architectural design or advanced certification question must directly address at least two distinct business requirements simultaneously to be considered valid. For instance, you might be asked to design a DHCP deployment that must reliably provide IP addresses while strictly avoiding conflicts with a legacy static server network. Learning to successfully balance multiple complex constraints at once is exactly what separates a basic technician from a highly skilled network architect. Taking a step back, you can clearly see how all these unique services beautifully integrate together to create a perfectly seamless user experience. A standard computer uses DHCP to get an address, DNS to find a website, and NAT to translate its private address for the public internet, all while the router uses COS to prioritize the traffic and Syslog to actively record the events. Every single one of these complex protocols operates completely invisibly to the end user, requiring a highly knowledgeable professional like you to design, configure, and maintain them. Mastering these core IP services is absolutely essential for passing your certification exam and thriving in any modern corporate IT department. Congratulations on successfully completing this highly detailed section on IP services and network management. To ensure these critical new concepts stick firmly in your long-term memory, I highly encourage you to immediately complete the attached practice test focusing heavily on DHCP, DNS, and NAT terminology. Remember that actively engaging with practice questions significantly improves your daily retention and rapidly boosts your overall confidence for exam day. You will find the practice test completely included right here with this lesson, so please take a moment to actively test what you have just learned. Maintain this incredible forward momentum, stay highly motivated, and I will eagerly see you in the next section where we tackle security fundamentals and threat mitigation. Welcome to the fifth section of our course, focusing on security fundamentals and threat mitigation. In this section, you will learn how to defend your networks from unauthorized access and malicious attacks. Network security is no longer an optional add-on for a company, but rather the absolute foundation of every modern IT infrastructure. Get ready to explore the essential tools used to protect sensitive data, because this knowledge is incredibly critical for both your certification exam and your future career. Let us jump right into securing our digital environments and making our networks safe. The foundation of all cybersecurity is built on three core principles known collectively as the CIA Triad. This simple acronym stands for confidentiality, integrity, and availability. Confidentiality ensures that only authorized people can read the data. Integrity guarantees the data has not been secretly changed while traveling across the network. And availability means the network is actually online when users need it. Every single security tool you will configure as a network engineer is carefully designed to protect at least one of these three fundamental pillars. Before we can protect a network, we have to understand the specific threats we are defending against. Modern networks constantly face automated attacks from malicious software, targeted attacks from dedicated hackers, and even accidental damage caused by untrained employees. A hacker might try to steal administrative passwords, flood the network with fake traffic to cause a system crash, or secretly redirect user data to a malicious server. Understanding how these common attacks operate allows you to proactively configure your routers and switches to block them instantly. The very first step in securing any network device is protecting the administrative command line interface with strong passwords. Out of the box, a brand new router has no passwords at all, meaning anyone with a physical console cable could completely erase the configuration. You must immediately configure secure passwords for both the console port and the remote access lines to prevent unauthorized users from gaining system control. Always remember the exam rule that standard passwords are automatically stored as highly readable plain text, so you must specifically enable password encryption to hide them in the configuration file. When administrators need to safely configure a router from across the building, they rely on remote access protocols, but not all protocols are created equal. In the past, engineers used an older protocol called Telnet, which dangerously sends all your typed commands and passwords across the network in completely readable plain text. Today, you must strictly avoid Telnet and instead use Secure Shell, commonly known as SSH. Secure Shell creates a highly encrypted mathematical tunnel between your computer and the router, ensuring that even if a hacker intercepts the traffic, they absolutely cannot read your password. As an organization grows rapidly, manually managing local passwords on 50 different remote routers becomes an absolute administrative nightmare. To solve this scaling problem, engineers implement the authentication, authorization, and accounting framework, universally referred to as AAA. Authentication simply confirms who the user is, authorization strictly limits what specific commands they are legally allowed to type, and accounting maintains a permanent, unalterable log of everything they did. By pointing all your network devices to one central AAA server, you can instantly grant or revoke administrative access for the entire company from a single location. Moving down to the local area network layer, switches are highly vulnerable to extremely specific attacks if they are not proactively secured. One incredibly common attack is a MAC flooding attack, where a hacker uses a basic software tool to blast thousands of fake MAC addresses into the switch in just a few seconds. This massive influx completely overwhelms the internal memory table of the switch, violently forcing it to act like a dumb hub and flood all future data out of every single port. Once the switch starts flooding traffic everywhere, the hacker can sit back and easily capture sensitive emails intended for other local computers. To completely stop MAC flooding attacks dead in their tracks, Cisco switches feature an incredibly powerful defense mechanism called port security. Port security allows you as the administrator to manually dictate exactly how many unique MAC addresses are legally allowed to communicate on a single physical switch port. If a hacker connects their laptop and tries to run a malicious flooding program, the switch instantly notices the rule violation and forcefully shuts the port completely down. For your certification, you must thoroughly understand the different violation modes, specifically the shutdown, restrict, and protect modes. Another highly dangerous local attack involves manipulating the automated IP address process we learned about in the previous section. In a DHCP spoofing attack, a hacker maliciously plugs in a rogue laptop and intentionally configures it to act as a fake corporate DHCP server. When innocent employees start their computers in the morning, the fake server quickly hands them an IP address along with a malicious default gateway address pointing right back to the hacker. All the employee web traffic now flows directly through the hacker's personal machine, allowing them to quietly intercept passwords before forwarding the traffic to the real internet. To decisively defeat these fake servers, network administrators implement a brilliant switch software feature called DHCP snooping. DHCP snooping forces you to manually identify which physical switch ports are actually connected to your legitimate, trusted corporate servers. All the other switch ports connected to regular employees are permanently designated as untrusted, and the switch will immediately block any DHCP server messages attempting to enter those untrusted links. This simple but highly effective configuration completely neutralizes rogue servers and is a heavily tested security concept on the CCNA exam. Hackers also actively exploit the address resolution protocol, which is the necessary system computers use to find the physical MAC address of their local default gateway. By sending completely fake ARP messages, an attacker can secretly tell all the local computers that the hacker's personal MAC address is actually the official router. The computers are mathematically tricked into sending all their private internet traffic directly to the attacker, creating a classic man-in-the-middle attack. This is extremely dangerous for corporate environments because the victims have absolutely no idea their private data is being intercepted. Just as we have a brilliant defense against fake DHCP servers, we have a highly effective solution for fake ARP messages called dynamic ARP inspection. This security feature works beautifully hand in hand with DHCP snooping to strictly verify every single ARP message flying across the local network. The switch actively checks the incoming ARP messages against a known, trusted database of legitimate IP addresses, instantly dropping any messages that look mathematically suspicious. Understanding how dynamic ARP inspection permanently protects the integrity of local network routing is a vital skill for modern security design. Protecting the local switch is highly important, but we must also strictly control the traffic flowing between different networks using access control lists. An access control list, universally known as an ACL, is essentially a highly detailed set of strict security rules applied directly to a router interface. As data packets attempt to enter or exit the physical interface, the router carefully reads the ACL rules from top to bottom, desperately looking for a mathematical match. You can configure these specific rules to permit safe network traffic or immediately deny unwanted traffic, making ACLs the fundamental building block of all network security. There are two primary types of access control lists you absolutely must master, starting with the basic standard ACLs. Standard ACLs are very simple security filters that only look at one single piece of information, which is the source IP address of the original sender. Because they are so incredibly simplistic, they act like a heavy blunt instrument, completely blocking an entire computer from reaching anywhere on the network, rather than blocking a specific software application. Standard ACLs use identification numbers between 1 and 99, and they are typically placed as close to the final destination as possible to avoid accidentally dropping legitimate data. When you need precise, surgical control over your corporate network traffic, you must step up and use extended ACLs. Unlike the standard versions, extended ACLs can actively filter traffic based on the source IP address, the destination IP address, and even the highly specific application port number. This means you could write a brilliant rule that safely allows a user to access web pages on a server, while simultaneously blocking that exact same user from transferring large files to it. Extended ACLs are significantly more complex to write, and they are always placed as close to the original source of the traffic as physically possible. There is one entirely invisible, but absolutely critical rule permanently hidden at the very bottom of every single access control list known as the implicit deny. This invisible security rule plainly states that if a data packet does not specifically match any of the custom rules you typed above it, the router must completely drop the packet. This means if you intelligently create an ACL with 10 rules that deny bad traffic, but simply forget to add a final rule permitting the good traffic, the router will silently block absolutely everything. Many exam questions will specifically test your awareness of this implicit deny concept, as it is the #1 cause of broken network configurations. While access control lists are absolutely excellent for basic network traffic filtering, modern corporate networks require the deep inspection capabilities of next-generation firewalls. Traditional ACLs only look at the outside delivery envelope of a data packet, but advanced modern firewalls can completely open the envelope and deeply inspect the actual application data hidden inside. This allows a hardware firewall to instantly recognize the digital signature of a known virus or actively detect a user trying to sneak unauthorized files out of the building. Firewalls beautifully combine multiple security technologies like intrusion prevention and strict malware filtering into one incredibly powerful defensive appliance. In today's highly remote workforce, employees frequently need to access secure corporate servers while sitting at a public coffee shop, which introduces massive security risks. To comprehensively protect this sensitive data over public wireless connections, network engineers configure virtual private networks, commonly known as VPNs. A VPN acts exactly like an incredibly secure, heavily encrypted digital pipe physically connecting the remote laptop directly into the corporate firewall. Even if a highly skilled hacker intercepts the wireless signal at the coffee shop, all they will ever see is completely unreadable scrambled mathematics, ensuring the corporate data remains totally confidential. Finally, we must briefly address the absolute physical security of our internal corporate wireless networks, as invisible radio waves easily travel straight through brick walls into public parking lots. In the distant past, early wireless networks relied on incredibly weak security protocols like WEP, which modern hackers can mathematically crack in literally 3 minutes using a basic laptop. Today, enterprise environments absolutely must strictly mandate Wi-Fi Protected Access version 3, or WPA3, which provides incredibly resilient mathematical encryption for all wireless frames. Securing the invisible airwaves floating around your office building is just as critically important as securely locking the physical front doors to your data center. Congratulate yourself for completing this highly essential section on security fundamentals and threat mitigation. I strongly encourage you to completely finish the attached practice test right now to solidly reinforce your understanding of access control lists and advanced switch security features. Taking these practice questions is a highly proven method to dramatically improve your long-term memory retention and heavily increase your overall exam readiness. Please remember that the comprehensive practice test is fully included right here with this lesson, providing a perfect opportunity for engaged active learning. Finish this exciting section strong, keep your incredible confidence high, and I will eagerly see you in the final section where we explore automation and programmability. Welcome to the sixth and final section of your CCNA Practice Preparation course, where we explore the incredibly exciting world of automation, programmability, and software-defined networking. In this lesson, you will learn how modern engineers use software tools and specialized code to manage hundreds of routers and switches at the exact same time. Understanding these modern concepts is absolutely vital, because the entire networking industry is rapidly moving away from manual configurations toward intelligent, automated systems. By the end of this session, you will feel completely comfortable discussing controller-based architectures and recognizing the powerful configuration management tools used in enterprise environments. Get ready to upgrade your skills for the future of networking, and let us explore how software is completely changing the way we build infrastructure. Historically, network engineers had to configure devices one by one using a console cable or a remote session, known as the traditional box-by-box method. If you needed to change a simple administrative password on 50 different switches, you literally had to log into all 50 switches individually and type the exact same command 50 times. This manual process is incredibly slow, highly frustrating, and massively prone to dangerous human errors that can accidentally break the network. Automation solves this exact problem by allowing you to write a single set of instructions on your computer and push that configuration out to thousands of devices instantly. The CCNA exam expects you to clearly understand the massive efficiency and accuracy benefits that automation brings to modern enterprise networks. To truly understand how software-defined networking works, you first have to understand how a traditional router thinks, which is divided into different functional planes. The control plane is the absolute brain of the router, responsible for running routing protocols like OSPF and mathematically calculating the best paths across the network. The data plane, on the other hand, is simply the physical muscle of the router, responsible for actually forwarding the data packets out the correct physical cables based on the control plane's map. In a traditional network device, both the highly intelligent brain and the physical muscle are permanently locked together inside the exact same physical metal box sitting in your server room. Software-defined networking completely changes this traditional design by physically separating the intelligent control plane away from the hardware data plane. Instead of having 50 independent router brains trying to talk to each other, engineers remove all the brains and combine them into one incredibly smart, centralized software controller. The 50 physical routers left behind simply become forwarding machines that wait silently for explicit delivery instructions from the central software controller. This centralized intelligence gives the software controller a perfect, bird-eye view of the entire global network, allowing it to route traffic much more efficiently than traditional isolated routers ever could. The absolute flagship software controller that you must know for the Cisco certification is called the Cisco Digital Network Architecture Center, or simply DNA Center. DNA Center is a highly powerful management appliance that acts as the single central brain for your entire enterprise local area network. Instead of typing complex command line codes, administrators simply log into a beautiful graphical web dashboard on DNA Center to completely manage their switches, routers, and wireless access points. DNA Center allows you to easily assign security policies, monitor network health, and instantly push software updates to every single device in your entire building simultaneously. For the central DNA Center controller to actually send these instructions down to the physical switches, they have to communicate using something called a southbound interface. The southbound interface is essentially the specialized digital language that travels downward from the software controller to the actual hardware devices sitting in the server racks. Historically, Controllers used a famous open-source protocol called OpenFlow to handle this southbound communication, but modern Cisco environments heavily utilize protocols like standard command line scripts or specialized NETCONF messages. For your certification, just remember that southbound interfaces strictly handle the downward communication between the central controller and the physical networking hardware. On the completely opposite side of the controller, we have the northbound interface, which allows the controller to communicate upward with other software applications. The northbound interface provides a way for custom computer programs, billing systems, or security software to ask the DNA center for detailed network information without needing a human to manually log in. For example, a custom security program could use the northbound interface to automatically tell DNA center to shut down a switch port if it detects a dangerous virus on the network. The exam heavily tests your ability to easily identify the clear difference between northbound interfaces pointing upward toward software and southbound interfaces pointing downward toward physical hardware. The actual mechanism that allows these different software programs and controllers to easily talk to each other over the northbound interface is called an Application Programming Interface, or API. An API acts exactly like a digital waiter in a restaurant, taking your specific data request to the kitchen and bringing the exact information you ordered right back to your table. Without APIs, different software systems written by completely different companies would never be able to securely share information or coordinate complex tasks. Learning how to properly identify and utilize APIs is quickly becoming the absolute most valuable skill any modern network engineer can possibly possess. The specific type of API that absolute dominates the modern internet and the Cisco exam blueprint is called a REST API. REST APIs are incredibly popular because they simply use the exact same standard web protocols that your internet browser uses every single day to load regular web pages. When you want to retrieve network information using a REST API, you simply send a standard HTTP message over the internet, and the server safely responds with the requested data. Because they use standard web protocols, REST APIs are universally understood by almost every single programming language, making them incredibly easy for network engineers to work with. When a REST API successfully brings that requested data back to you, it has to be formatted in a way that both humans and computers can easily read, which brings us to JSON. JavaScript Object Notation, widely known as JSON, is a highly lightweight text format used almost exclusively to structure and store API data. JSON organizes information using a very simple system of key and value pairs, tightly wrapped inside curly braces, making it look almost like a highly organized digital dictionary. The certification test will absolutely expect you to look at a block of JSON code and correctly identify the specific keys and values being presented. As networks continuously grow into massive global environments containing thousands of devices, network engineers rely on specialized configuration management tools to automate their daily tasks. These powerful tools completely eliminate the need to manually configure devices, allowing you to rapidly deploy identical configurations to hundreds of routers in just a few seconds. By keeping all your network configurations safely stored as text code on a central computer, you can easily track exactly who made a change and instantly reverse it if something breaks. The three major configuration management tools you must explicitly know for the exam are Ansible, Puppet, and Chef. Ansible is currently the absolute most popular configuration management tool in the networking industry because it is incredibly simple to set up and start using. The biggest advantage of Ansible is that it is strictly an agentless tool, meaning you absolutely do not have to install any special background software onto your Cisco routers to make it work. Ansible simply connects to your network devices using the exact same standard secure shell protocol that you would normally use to log in manually. You write your automation instructions in highly readable text files called playbooks, and Ansible instantly connects to the devices and executes your commands precisely as written. Puppet is another highly respected configuration management tool, but it operates fundamentally differently than Ansible because it typically requires you to install a software agent directly onto the network hardware. Puppet uses a centralized server called a Puppet Master that constantly communicates with these background agents running securely on your routers and switches. Instead of telling Puppet exactly how to configure the router, you simply describe how you want the final router configuration to look, and Puppet mathematically figures out the specific commands needed to make it happen. You should strongly associate Puppet with installed software agents and highly continuous configuration monitoring for your exam scenarios. Chef is the third major configuration management tool you need to recognize, and it is heavily favored by professional software developers who are comfortable writing more advanced code. Like Puppet, Chef typically requires you to install a software agent onto your end devices, which constantly checks in with a central Chef server for new instructions. Chef uses a unique culinary naming theme, where you write your configuration instructions in files called recipes, and you group those recipes together into larger collections known as cookbooks. If you ever see an exam question talking about configuration management using recipes and cookbooks, you can confidently select Chef as the correct answer. When using these various automation tools, you will encounter different text formats used to write the actual code, primarily JSON, XML, and YAML. We already know JSON uses curly braces and is widely used for REST APIs, while XML uses older, bulky text tags that are quite difficult for humans to quickly read. YAML is the absolute favorite format for writing Ansible playbooks because it intentionally removes all the confusing brackets and tags, relying entirely on clean text and strictly measured spaces to intuitively organize the data. The CCNA will definitely test your ability to visually tell the difference between the curly braces of JSON and the clean, spaced lines of YAML. To fully utilize these advanced software controllers, modern data centers use the heavily organized spine and leaf physical topology we briefly mentioned in the very first section. In a software-defined data center, the central controller actually treats the entire spine and leaf physical network as one giant, unified fabric rather than 50 individual switches. This fabric design completely eliminates the need for older, dangerous loop prevention protocols like spanning tree, allowing every single physical cable to actively carry data at maximum speed simultaneously. Understanding that modern controller-based networks absolutely thrive on highly redundant spine and leaf physical layouts is a critical architectural concept you must remember. Bringing these centralized software concepts out of the local building and across the global internet introduces us to Cisco Software-Defined Wide Area Networking, or SD-WAN. Historically, connecting global offices together required highly expensive, dedicated physical circuits leased from telephone companies, which took absolutely forever to install and properly configure. Cisco SD-WAN allows you to securely combine cheap public internet connections with expensive private links, using a central software controller to dynamically route traffic over the fastest available path in real time. SD-WAN massively reduces corporate telecommunication costs while heavily increasing application performance, making it a highly tested topic on the modern blueprint. As we confidently hand more control over to automated software, network security actually becomes significantly easier to manage consistently across an entire enterprise. Instead of hoping a junior engineer remembers to manually type an access control list correctly on 50 different switches, the DNA center controller automatically pushes the exact same perfect security policy everywhere. This guarantees absolute consistency, immediately eliminating the dangerous configuration gaps that clever hackers often exploit to gain unauthorized access to a corporate network. You should always view network automation not just as a way to save valuable time, but as a massive, critical upgrade to your overall security posture. You might feel slightly overwhelmed by all these new programming concepts, but remember that the CCNA exam absolutely does not expect you to be a professional software developer. You do not need to know how to write complex Python scripts from scratch, but you must strictly understand the core vocabulary, recognize the data formats, and clearly explain what the automation tools actually do. Focus your final study efforts on understanding the functional differences between the control plane and the data plane, and the exact physical roles of northbound and southbound interfaces. Mastering these highly specific definitions will guarantee you easily earn the automation points on your certification test. Congratulations on successfully completing this final section, and a massive congratulations on finishing all the lessons in this comprehensive exam preparation course. To firmly cement these modern automation and programmability concepts, I highly encourage you to complete the attached practice test right now while the terminology is perfectly fresh in your mind. Remember that actively answering practice questions dramatically improves your memory retention and guarantees you're absolutely ready for exam day. Please ensure you complete the practice test included right here with this lesson to accurately measure your incredible progress. You have shown fantastic dedication to active learning throughout this entire journey, and you are now thoroughly prepared to conquer your certification exam and massively advance your career.